Interested in airships? Ever wonder what the future of airship development would be like? If you're like me, you might have gone looking into present and future airship concepts. What you would have found is a curious combination of pie-in-the-sky computer artist concepts, perfectly technical studies in possible vehicles and their utility, as well as precious little physical development. Airships may be my case study of interest, but really the relevant questions would sound very familiar. Why is this technology not more widespread? What does it take for it to become widespread? What obstacles and challenges stand in the way of this cool idea impacting everyday life? There's a saying I keep hearing in regard to developments in the industry of vehicle and vessel technologies. Believe nothing you hear and only half of what you see. Such is how precarious any project's success can be. Take airships, for example. It is and was very easy for writers and editors of popular science publications to imagine airships as a wondrous technology, just a couple steps down from anti-gravity, fit to make our human lives interesting again in the most novel ways. Credit goes to their artists for the stunning visuals. However, the process needed to make a proper airworthy airship faces real tangible challenges in the economics and logistics of physical development and the engineering challenges. To briefly touch on the economics of development, it seems to me to be a chicken and egg situation. To adopt a technology, it must prove useful. To prove a technology useful, it must be adopted and used to some extent. Usually this means starting at a small scale and mission scope, proving a concept works and can be adopted at a larger scale and used in a larger economic context. Alas, some technologies only work or provide profitable returns at larger scales and scopes. Too small and a concept can fail, belying its possible larger utility. What this seems to require is that small-scope development cannot afford to run afoul of mission creep, and must master each link in the chain of basics in operations. How a vehicle can be conceived to master basics of operations, in our case handling and using an aerostatic dirigible vessel, leads into the engineering challenges, where I myself have made some study and will constitute the bulk of my commentary. Long before an airship can be considered for its gizmos and gadgets, equipment and payloads, the very first parameter for consideration is the most fundamental. What lifting gas should they use? For relative simplicity, hydrogen or helium. Everything else must follow from this decision. To do a real comparison between hypothetical hydrogen and helium airships, we'd have to set some parameters and boundaries. In one case, we can have the same airship design, but evaluate its capacity with the only difference between them being a change in lifting gas, hydrogen and helium. Thus, the payloads will be different. In another case, we can have two different airship designs meant for the same net payload, and assumed to have the same ratio of structure to displacement, but necessarily needing different amounts of displacement. Thus, one will be bigger than the other, with practical consequences entailed. To make the calculations viable, some unrealistic assumptions had to be taken for measuring the properties of the gases in question, air, hydrogen, and helium. To account for more realistic conditions merely requires applying modifiers to the variables in question. Changes in density under variable atmospheric conditions, i.e. pressure or temperature, change all gases equally. But the end airship design may be significantly altered. As an example, any airship meant for lower density conditions, high altitude, higher temperature or humidity air, or using a less effective lifting gas, helium versus hydrogen, will necessarily be bigger by degrees than a hydrogen airship in standard atmosphere. The most fundamental limiting factor for an airship design is its gross displacement, or how much mass in air it can displace with its own lower density lifting gas. The only way that gas is contained is with a structure: fabric, tension lines, solid space frames, power plants, controls, and crew accommodations, among others. Anything that's needed to make a water-bound vessel seaworthy, much of that and more would be needed for an airship, and would contribute to its empty or non-disposable mass. The payload then, what includes useful equipment, valuable cargo or passengers, and ballast or disposable mass, takes up the rest of the air displacement. This sets just how much use you can get out of your airship. The first comparison to make is how the payload ratios decrease with increased empty weight ratios for each airship, hydrogen and helium, assuming the same displacement. Naturally, the helium airship's payload capacity starts at less than hydrogen's, in the case of no empty weight. Imagine a party balloon. As the empty weight increases, the payload capacity for both goes down. For the helium airship, the empty weight ratio that approaches around 86% leaves no capacity for payload lift, while the hydrogen airship only has a little more lift left in it. This is why minimizing the empty weight is crucial to airship design, but also for the vastly greater expense and lesser access, helium is also a poorer choice for lifting gas in airships. Every other gas that performs worse, steam, hot air, nitrogen, is also vastly more accessible while dealing with the same challenges of fire prevention. The next comparison is how two airships of same displacement, one hydrogen, one helium, can differ in payload for the same empty weight, or in required empty weight for the same payload. Making the calculation and reducing the equations yields two similar analogous equations for how the ratio of a helium to hydrogen airship's payload or empty weight relates to that of the hydrogen payload or empty weight ratios. The results are thus. If a hydrogen airship can only achieve neutral buoyancy with a payload ratio as small as 7% of gross displacement, then a helium airship just will not fly at all. A hydrogen airship which manages somewhat greater payload ratios means the helium airship suffers marginally less degradation of payload. This is a case where a modernized airship using advanced materials and structural engineering that can minimize the needed structure also allows for a less painful switch to helium is desired. However, if anyone has ever thought that helium has 98% of the lifting capacity of hydrogen, therefore replacing it is essentially one-to-one in performance, look at the end of the graph. The statement is true in but one sense, where the airship in question manages all payload and no structure. That is party balloon dimensions. The final comparison takes two airships that need to carry the same payload, and for simplicity are limited to the same empty weight. But the helium airship by necessity has to have greater air displacement. This is the scenario where one accepts that for a hydrogen airship and mission payload, substituting for a helium airship requires accepting an airship with a comparatively sparser structure. After calculations and simplifications, the end result is that, assuming the best case scenario of a really advanced low-weight, high-strength structure and empty weight, the helium airship must, at minimum, have 8% greater displacement. Anything less optimal and the helium airship must get progressively larger to make up for the lost efficiency that the hydrogen airship had. This might not be a problem with a large enough airship and a correspondingly enough helium to inflate it. Unfortunately, The expense and scarcity of helium doesn't lend itself to making many progressively larger helium airships. If you have a size limit on making airships, hydrogen would be the most viable, and being forced to only use helium would guarantee an economically non-viable vessel. This graph is only slightly different from the previous graph, comparing the relative payload versus empty weight of helium and hydrogen airships. The relationship holds true even when allowing a helium airship to be bigger. Despite the utter lack of airships plying the skies today, there were and are real advancements in power, structures, and materials as applied to helium blimps, such that we're no longer limited to Goodyear blimps covering sporting events. Now we have Zeppelin NTs giving tours, at least I think we still do. Suffice it to say, helium airships are viable vehicles to operate in this day and age, as long as they're not pushed very far. Alas, it says something about our lack of airship building pedigree that in this modern day and age, we typically make barely viable vehicles of this type, and not anything larger, more profitable, and utilitarian. If, in the last 25 years or so, you've perused publications for popular science, technology, or mechanics, you might have occasionally seen concepts, often just concept art, of supposed future airships, using various additions to the classic pure ellipsoid body. Very rarely are these hypothetical designs sold on being larger, and thus taking advantage of the square cube law, but rather they're sold on having the addition of rotors or wings, or being lifting bodies. It is such that their capacity to be useful is not dependent on the actual buoyant lift of the helium. Adding structure for rotors or wings is a cost and weight, and one that the square cube law works against getting bigger. So instead of helium airships being fully steerable vessels of the sky, they essentially become malformed aircraft or rotorcraft with a balloon envelope stuck to them parasitically. I think I read somewhere that forcing airships to use only helium was the best thing that ever happened for airlines, at least where the competition was concerned. I expect there's far more technicality than can be simplified to such a statement. Nevertheless, forcing airships to only use helium, figuratively, weighs them down, where designs and operations are concerned. Helium is so rare that sourcing it is expensive, so an airship can't make use of venting the gas overboard to reduce lift when ballast or fuel is consumed, or when a payload is offloaded. One attempt to make up for this restriction involved underinflating airships down to the minimum needed lift to fly. You would see this in all current Goodyear blimps. The spare volume is taken by air-filled ballonets that maintain the envelope inflation. The major shortcoming is no payload can be offloaded or deployed because no gas can be vented to find equilibrium. And if the atmosphere becomes too rarefied, gas can't be vented, so the airship has to descend, even to the ground. Another attempt to get around this is to recover ballast from water vapor in the exhaust of combustion engines. The machines to do this were heavy and bulky, and the airships that used them, Akron and Macon, had to be large to match. Given that design philosophy was never repeated, speaks against its efficacy. One method that has yet to be tried, however, is using hydrogen as an anti-ballast. So long as helium is mandatory and expensive, let the hydrogen be the disposable lift for when the fuel and ballast is expended. The division of lift could have the hopefully non-leaking helium supporting the largely unchanging empty weight, while the hydrogen matches lift with the disposable ballast, consumable fuel, and removable cargo. Ideally, the hydrogen can be used in multiple different ways. If venting hydrogen to reduce lift is necessary, then it would help to use that hydrogen in a fuel cell for electricity, and water to recover ballast. In reverse, Ballast water can be recovered into lift by electrolyzing it into hydrogen, oxygen excluded. If power and opportunity allows, water can be collected in flight and increase options for extending a flight. None of these things can be done with helium, not without alternate means of buoyancy control. Without buoyancy control, a helium airship, where helium can't be vented except at great cost, can only deal with excess lift or deficient lift in one of two ways: vertical rotor power or with aerodynamic lift. Since rotor systems with increased lift capacity also increase in weight with size, these are only helpful on the smallest airships, i.e. the Goodyear blimps with vertical vectoring fans. For larger vessels, it's more useful to use the airship's aerodynamic body for lift. What works against a large helium airship is that to use lift, it needs airspeed. And if it needs airspeed, then to take off or land, it needs a runway. An airship with proper buoyancy and ballast control shouldn't need a runway at all, just a clear area to land or dock. But by limiting an airship to indispensable helium and no such controls, the airship is truly consigned to the operation and flight profile of an airplane, and is invariably disadvantaged by the comparison. One possible method of fire prevention for a gas bag holding hydrogen is to use one or two different gases as a fire retardant. Mixing both nitrogen and carbon dioxide with the hydrogen might be sufficient, but there's a method of greater control. Around the main gas bag, two smaller bags, both dorsal and ventral, hold the other gases. Nitrogen would be held in the dorsal bag, and carbon dioxide in the ventral. If and when fire catches on the skin, above the midpoint, nitrogen, and below, carbon dioxide, vent outward to snuff out the flame, protecting the hydrogen from outside oxygen and ignition, at least for the duration of the gases. The YouTube channel Roballoon portrayed this method, and I think it's a viable step forward for preventing fire in airships. Another possibility for preventing fire in a hydrogen gas bag would be to make the skin retardant of fire. Typical methods for making such structure fire retardant would be too heavy for an airship's skin, so we'd have to get creative. Imagine modern plastic-based closed-cell foam, but with cells of nitrogen and carbon dioxide or other retardant chemicals, as well as liquid sealant. The mode of operation sought is that a puncture to the gas bag breaks cells, releasing gas to snuff open flames of oxygen, and epoxy resins are released to expand, foam, and solidify in the path of the puncture, minimizing leaks and intermixing of oxygen with hydrogen. If we size an airship to use helium, but can't spare the expense, then there's a mathematical calculation to show just how much displacement in air mass can be dedicated to hydrogen, nitrogen, and carbon dioxide. Naturally, the bulk of the gas has to be hydrogen for the lift, but by taking the end mass of both nitrogen and carbon dioxide to be equal, we can also calculate the mass ratio of those gases to the overall displacement. Naturally, with denser carbon dioxide, it takes less of the displacement compared to the nitrogen. Now I think is a good time to start relative comparisons of airship proposals and projects over the years of the early 21st century. Maybe then it will become apparent how widely varied expectations of airships run up against the engineering considerations I've outlined so far. Going all the way back to 2005, it's the midst of the American War on Terror, and the U.S. military is looking for a solution to transporting materiel and personnel en masse. Enter DARPA's funding for the airship transport Walrus. Despite the impressive numbers of individual innovative technologies expected to be packaged with the airship, This project has long been consigned to the shipbuilding equivalent of vaporware. As revolutionary as this was expected to be, and expanded military spending might have been cause for optimism, the basics of making an airship operational were not satisfied. 2007. DARPA provides some funds to a company, Aeros, to improve upon demonstrations of their buoyancy control technology, which, despite the utter lack of disclosed technical details, is supposed to precisely control buoyancy without the need of disposable ballast. This is supposed to allow for plenty of space for passenger accommodations in a configurable cabin much larger and better appointed than a typical passenger airliner. Fast forward to 2013 and there is a fuller scale prototype being tested and handled, now with hovercraft air cushions as landing gear. The vessel and the landing gear may work just fine, but if the control of static heaviness system doesn't make it at least economically viable, then the lack of copycats of technology licensing customers will leave this only as a niche demonstrator of revolutionary tech. Is it still revolutionary if no one tries to copy it? To be clear, this is all in pursuit of preserving the use of helium and not losing it to the atmosphere uselessly, since any other form of ballast and buoyancy control would be unfeasible with that lifting gas. 2008. A Canadian firm reportedly starts collaboration with Boeing to make a heavy lift airship fit for lifting and transporting cargo in remote, unprepared areas of wilderness. This is a rotostat, and its four-rotor system would rival or rather exceed the size and capacity of the largest serial production helicopter past and present, the Mi-26. In accordance with keeping to helium, the envelope displacement would presumably hold enough to uphold the weight of the rotor system, which would in turn provide the lift for actual cargo. Notwithstanding how quickly a rotor system increases in weight with size, keeping the envelope relatively small means there's no safety margin for disposable ballast or disposable lift in hydrogen, so all adjustments are entirely dependent on controlling lift from the rotors. In fact, I suspect weight for a large cargo-carrying multi-rotor go up even faster than what would concern a single-rotor helicopter. That's because the structure has to support not only the lift of the rotors, but also the bending moment of the rotors that would have them crunch the center structure and careen into each other, destroying the airship. Which is to say, the structure presented in computer artistry shows a rotor support frame too sparse not to buckle, and a vestigial helium envelope too small to support what's needed. No points for guessing this went nowhere. 2017 to at least 2018, a company called EGAN Airships literally tried to combine a plane with a blimp, a so-called plimp. No joke, they expected to attach an envelope roughly the size of a Goodyear blimp to an electric hybrid tilt-wing aeroplane, or on a smaller scale, a drone. Ostensibly, the blimp part would let the plimp fly slow, or increase its flight range by offsetting some of the plane's weight, never mind the balloon-like drag. There were two considered scales, first a small-scale uncrewed aircraft, and a conceptually larger passenger-carrying variant. What little information is available conveys to me this is very much like a classic Goodyear blimp, but with the gondola expanded to accommodate tilting wings, rotors, and an airplane empennage. Can you see the issue? The plane part of the plimp suggests an aircraft that needs high speed to fly properly, but can't on account of the bulbous envelope. Every other airplane would have better performance. And the blimp part of the plimp? Were it not truly vestigial in the plimp flight mission, A larger envelope could uplift heavier loads, or better handle lesser loads where ballast is mindfully managed. It might even allow for hybrid electric tilt-wing propulsion to improve flight handling and energy efficiency at speeds where airplanes would stall, or, if not faster speeds, then at least useful speeds, where minimizing power requirement and fuel consumption is useful. Alas, where airships are concerned, there really is such a thing as too small. I could find no other information for development since. The first comparative success story I can point to is called the Hybrid Air Vehicles Airlander 10, which was born out of a U.S. military project called Long Endurance Multi-Intelligence Vehicle. This military project was a collaboration between the American company Northrop Grumman and the British company Hybrid Air Vehicles. Alas, the LEMV project was cancelled, so Hybrid Air Vehicles rebought the single prototype and has been, since 2013, been developing and testing the prototype until its retirement in 2019. Out of its testing history, statements in 2020, 2022, and 2024 suggest there will be a sustained production run of a version of the Airlander 10, which seems to be the closest so far that an airship concept has gotten to making a real-world economic impact since the Goodyear Zeppelin NT. This airship, uncharitably dubbed the Flying Bum, is a Dynastat hybrid airship, which uses both aerostatic lift from helium and aerodynamic lift from forward motion. One source I found says it doesn't require a purpose-built runway for all the performance benefits it's due to provide. As successful as I should hope this airship design becomes, I can't help but predict it's going to inherit the ball and chains that are helium-only lifting gas and runway dependency. And unless it will be restricted to remote open fields for its operations, it's probably going to use the kinds of runways that other airplanes use. And I'm not confident it won't suffer for the comparison. But it'll definitely turn heads. 2022. And this is what I'm talking about when airships become set dressing and pie-in-the-sky concepts. It should be clear to me, you, and everyone looking that this is not a serious vessel. It's a yacht turned spaceship. Pier Paolo Lazzarini air yacht concept makes a catamaran out of 2 airship envelopes, and in addition adds the usual refinement of yacht-based leisure that completely takes up the volume of the envelopes. There can be no pretense that this holds any helium worth any amount of lift. It might float on water, but floating through the air is mostly aspirational. This wouldn't even be worth a look were it not for the fact that this contributes to airships being portrayed and seen as unrealistic as a transportation and infrastructure technology. Also in 2022, a Swiss company called Air Yacht presents this concept by engineers Guillaume Hody and Mathieu Ozane, as well as French yacht designer Frank Darnay. While it seems to be just another yacht with a vestigial helium airship, it seems the design leans closer to the proper engineering that determines the envelope must be substantially large to achieve the proper lift, even if the advertising ducks the engineering question of ballast and buoyancy control by means of the phantom air buoyancy system. Depending on how much air mass displacement is taken up by the yacht gondola, the change in buoyancy would have to be substantial indeed, so the airship isn't lost to the sky whenever the yacht detaches. The computer artist's concept also does well to recognize the need for distributed propulsion in multiple propellers and fine control that would be needed for flying the vessel. Even if provisions for ground handling are totally absent, again, the mythical air buoyancy system is supposedly supposed to take care of that. It still feels like another vehicle, if you will, for the portrayal of yacht and interior design rather than an advancement in airship building. Ostensibly, the design has been worked on since 2017, and the first orders are due to be fulfilled by 2016. But without an actual prototype vehicle circa 2025, that should be very hard to believe. Technical details are scarce, and I expect news of progress will remain scarce to non-existent. Finally, 2023, and here's a new airship we actually get to see. Brought to you by Google co-founder Sergey Brin and the company he founded, LTA Research, in 2015, comes Pathfinder 1, a fully constructed airship with a rigid frame, helium gas, and a certificate for flight testing. Fingers crossed if a professional corps of flight and ground crew can get a handle on this design of vessel. Even as it's stated to use helium, there's some hearsay to believe that it can be used with hydrogen lifting gas, so here's hoping everyone's up to speed on fire mitigation as well. With an actual prototype to work with, it would be interesting if a Google founder can gather the proper talent together to make this a viable airship design and not just another one-off. This one is presented by a company, H2 Clipper, which is invested in producing and distributing green hydrogen. It's a concept for an all-hydrogen, lifted, and powered airship. Circa 2025, the concept is still in the computer-aided designing and fluid dynamics stages. But what I find interesting is if you peruse their website, they have a list of issued patents, including the ubiquitous buoyancy control system, that suggest they may actually prototype an airship and the hydrogen pipeline infrastructure that's related to their business. This is assuming, of course, the patents aren't just for denial to other possible competitors. Based on the engineering side of the presentation, they seem cognizant of the aerodynamics and operations of their airship as a cargo carrier, flying point to point between factories and distribution centers, for whatever cargo is concerned. I suspect liquid hydrogen would be their first cargo of choice for their clients. But they still don't have a prototype to fly, so just like their liquid hydrogen distribution development, it's still a dream in the pipes. If you remember the record-breaking flights around the world by balloon in 1999, and then by solar-powered airplane in 2016, then if we take Aero Airship at their word, Bertrand Piccard will do it again with two other crewmates in a solar-powered airship called Solar Airship 1. So far, everything on presentation is CGI, but I'm willing to trust in Piccard's reputation as a flying pioneer, that this project is a serious attempt at a functional airship, especially for a record-breaking non-stop round-the-world flight. Just like all other aspiring concepts, this one will use helium, but in a novel change, it will also use hydrogen and pure solar power, which I trust means that Piccard and crew will take advantage of the hydrogen as a disposable lift anti-ballast to run counter to any ballast they may need to jettison in flight. In aspiration, the program also states interest in using water and solar power together, as a kind of lift gas to ballast exchange system I've imagined myself for a while. Part of me says there's no physical prototype yet, so don't get your hopes up. Another part of me remembers Solar Impulse 2 in Popular Science, years before it was made real, and then succeeded in its round-the-world non-stop flight. Even after all these years, I'm willing to go on a little faith. We shouldn't forget that in the quest for the future airship, Lockheed Martin wasn't left out. In the same military competition for the long-endurance multi-intelligence vehicle, Lockheed designed, built, and tested the P-791. Whereas the Grumman airship was a double-lobed envelope, this one by Lockheed is triple-lobed. It's also a hybrid Dynastat airship, using aerodynamics and running takeoffs to get airborne and perform its flight mission. When the LEMV program was canceled, the airship was redesignated as LMH-1 and was being reconfigured for prospective commercial use. As of 2023, the prototype airship and intellectual property related to it were sold by Lockheed to AT2 Aerospace for their own airship development project called the Z-1. Now, circa 2025, AT2 Aerospace is hyping the Z-1 and its iterations as the future in cargo transport to remote regions. With a likely nebulous air buoyancy control system, air cushion landing gear, and an aspiration for hybrid electric propulsion, the Z-1 might just be on a similar track to fruition that the Airlander 10 seems to be on. It's also subject to the same restrictions in operation that comes with exclusively helium lift and not purely aerostatic lift as well. But hey, if the development cycles of two new airships reach fruition and come upon the same limitations at the same time, I like to think it's twice the odds that solutions will be forthcoming. Now, finally, for another Sky-pie, but with a modicum of real-life testing. Ostensibly since 2012, Flying Whales has been working on its own bid for a future airship, the Large Capacity Airship 60-ton, or LCA-60T. There is already a great deal of overlap in the presumed role of such an airship, so it doesn't bear repeating here. What's interesting to me is that for the mostly computer-generated assets, belying the lack of assets in reality, there is plenty of detail that shows genuine engineering concern for making this hypothetical vessel work. A rigid frame that supports helium gas bags that must expand or contract. Multiple sets of propellers, sized and positioned to maintain fine flight control for its cargo transferring flight profile. And a structurally reinforced cargo bay designed to load and offload cargo via cable without landing the airship, which, if properly developed as an airborne procedure, can help break the design free of runways, as airships should be. Believe nothing you hear also applies to concepts still restricted in the virtual realm. Nonetheless, this seems like an awe-inspiring project, if the physical, practical considerations can be ironed out in other projects, like the previously covered Airlander, Z-1, and Pathfinder 1. And with that, I've satisfied my itch for engineering airships, so fair winds and clear skies to you all.